Hi everyone, in this video we are graphing a rational function. G of x is equal to 2x squared minus 9x minus 5, all divided by the quantity x minus 3. Now remember, we can identify this as a rational function because we have a polynomial here in the numerator and a polynomial in the denominator. So anytime you have a polynomial divided by another polynomial, that's a rational function. And remember, the root word in rational is ratio. So it's a ratio of two polynomial functions. So to begin graphing this rational function, I always recommend that you start with the domain. What are all of the possible values we can have for x? And in this case, remember that the denominator of a fraction can never equal 0. So x minus 3 cannot equal 0, meaning x cannot equal 3. If we substituted in a value of 3, we would get division by 0. So my domain is all real numbers except for 3. So in interval notation, we write that as negative infinity to 3 and 3 to infinity. Now I like to write my domains in interval notation because I can see there are two intervals here, and that's going to correspond to my graph. I'm going to see two pieces of my graph. My graph is going to contain two pieces or two branches. So after the domain, we need to find the vertical asymptote or vertical asymptotes if there's more than one. And to do this, it's really important that you simplify the function first. So for this function, we're going to see if the numerator factors. So I'm going to do my factoring over here off to the side. Now, some of you may factor using the AC method, and some of you may factor using guess and check. I prefer guess and check myself, so I'll demonstrate guess and check as I try to factor 2x squared minus 9x minus 5. So in the first position, I know it has to be 2x times x because that's the only two factors that will multiply to give me 2x squared if we are working with whole numbers. Now in the last position, I know that these two values have to multiply to give me negative 5. And I really only have two options. I could do a positive 5 times a negative 1 to equal negative 5, or I could do negative 5 times a positive 1. So I have one of these two pairs. I just have to figure out where the numbers go so that it will indeed multiply out to give me 2x squared minus 9x minus 5. So I'm just going to demonstrate the trial and error method here in case you need the review. You can always fast forward if you already have it factored. Let's pretend like I think it's a positive 5 and a negative 1. Now I'm going to check this by doing first, outside, inside, last. I've already checked the first and the last, so I'm just checking the outside and inside. So outside would be 2x times negative 1, which is negative 2x. And inside would be 5 times x, which is 5x. Now 5x and a negative 2x will not add to give me negative 9x. So that tells me that I've chosen incorrectly. So I'm going to erase. And perhaps I have the right values, I just have them in the wrong places. So positive 5 and negative 1 is what I tried. So I'm going to stick with that, but I'm going to put the negative 1 first and the positive 5 second. Outside now is 2x times 5, which is positive 10x, and inside is a negative 1 times x, or negative x. And now you'll notice I'm really close because a negative x plus 10x is a positive 9x. I'm very close, but I actually want negative 9x. So that's a nice easy fix because that tells me that I just need to change my signs. So instead of a negative 1 and a positive 5, we'll try a positive 1 and a negative 5. So one more time, outside is 2x times negative 5, which is negative 10x, and inside is that positive 1x, and that indeed will add to a negative 9x. So my factors are 2x plus 1 times x minus 5. And you'll notice now that I cannot simplify this expression at all. We don't have any common factors on the top and the bottom. So what that tells me is I do not have any holes. If you had a common factor, that means that you would have a hole in your graph, but we don't have common factors, so we have no holes. So my vertical asymptote is just going to be that value that caused the denominator to be 0. In this case, x equals 3. I recommend that you graph as you go. So if you get a characteristic, go ahead and put it on your graph. In this case, here's my vertical asymptote of x equals 3. Next, we'll look for a horizontal asymptote. Now, horizontal asymptotes depend on the degree. The degree of the numerator is a 2, and the degree of the denominator is a 1. The degree is that highest exponent of a variable. So degree 2 on top, degree 1 on the bottom. And when the degree on top in the numerator is larger than the degree in the denominator, that means we do not have a horizontal asymptote. We've got no HA. In this case, that is because as x increases and becomes an infinitely large number, the numerator, which has a 2x squared as its leading term, that will always be larger than the denominator, which has an x as its leading term. The numerator will always be much, much larger. So therefore, as x becomes a very large number, the output, y, the y values also become very, very large numbers. That means that the end of the graph is not going to ever level off, and it will not have a horizontal asymptote. So this happens to be the special case where the degree of the numerator is 1 greater than the degree of the denominator, and that produces a slant asymptote or an oblique asymptote. To find the slant asymptote, we're going to go ahead and do our division. So we're going to divide the denominator into the numerator. So in this case, we're dividing x minus 3 into 2x squared minus 9x minus 5. So this is with long division, and certainly long division is an option. However, if you prefer, you can do synthetic division because our divisor right here is linear. And when that divisor is linear in the form of x minus or x plus a constant, then we can do synthetic division instead, which is certainly my choice. So if you take that divisor of x minus 3 and set it equal to 0, you're finding the 0 of the divisor, which in this case is 3, then 3 is the value that is going to go in the box for your synthetic division. And our coefficients are 2, -9, and -5. Again, many textbooks will show long division here. I just prefer synthetic. So we drop down the 2, we multiply 2 times 3, which is 6. We add straight down, which is -3, multiply by what's in the box, and then add straight down. So -14 is my remainder. But remember, with our synthetic division for slant asymptotes, we don't need the remainder. You can ignore the remainder. So the 2 and the 3 in this case, because we were dividing an x into an x squared, the result is going to be linear. So my answer will be 2x minus 3. In other words, this is the line y equals 2x minus 3, which is the equation for your slant asymptote. Y equals 2x minus 3. So I want to graph this line. The y-intercept is -3, and the slope is +2. So I'll travel up 2 and right 1, and I'll keep doing that repetitively. I could also go down 2 and left 1. And I recommend that you have a straight edge if you're doing this on paper, because this is definitely going to be a straight line, what we call our slant asymptote. So now we need to find some exact points on our graph. So I would start with your x and your y intercepts, and you can do these in any order. It doesn't make a bit of difference. So for any function, if we're looking for x-intercepts, remember that's where the graph crosses the x-axis. We're going to let y equal 0, because if we're on the x-axis, we know that the y value will be 0. So I'm going to substitute 0 in for y. Now looking back at the original function, we have the original function here, and then we have the factored form here. And I'm going to choose to use my factored form. And with a little bit of practice, once you do a few of these examples, you'll see why the factored form is so handy. Because when I go to solve this equation, I know that I would multiply both sides by x minus 3 to get rid of this x minus 3. And if I multiply the left side by x minus 3, 0 times x minus 3 is just 0. So I'm really just left with the numerator, which I would have to factor eventually. So I might as well choose the factored form since I've already factored it. So if I set each of my factors equal to 0, I solve these resulting equations, and that gives me x is -½ and x is equal to 5. So I have two x-intercepts. One is -½ 0, and the other will be 5, 0. Remember, I recommended that you graph as you go. So let's plot those. -½ 0 and 5, 0 are the two places where this graph will intersect the x-axis. So lastly, we need to find that y-intercept, and we'll do that by letting x equal 0. So in this case, we're finding g of 0 because we're plugging 0 in for x. And again, you could use the original function or you could use the factored form. Here, it's actually easier to go back to the original function, the 2x squared minus 9x minus 5. So 2 times 0 squared minus 9 times 0 minus 5. And that was divided by x minus 3, which would be 0 minus 3. So that's going to give me -5 divided by -3, which is a positive 5/3. So my y-intercept is 0, 5/3. Now remember, 5/3 is really 1 2/3. So 0 and 1 2/3 I need to plot. So up 1 2/3, I'll just estimate approximately where that is. 0, 5/3. Now we want to put the pieces together, finally finish this off. What is this graph going to look like? Now, some of your instructors might want to know if your graph is going to actually intersect its asymptotes. So let's discuss that briefly. Remember that vertical asymptotes can never be intersected. We can never cross through this vertical line of x equals 3 because if x is 3, then we would have a division by 0. Not allowed. However, it is worth noting that sometimes slant asymptotes, you can intersect a slant asymptote. So if you're interested in determining whether your graph is going to intersect its slant asymptote, then we have to do one little extra step here. So because the graph of my slant asymptote, the equation is y equals 2x minus 3, we have to check and see if the asymptote, 2x minus 3, will ever equal our original function, which was the 2x squared minus 9x minus 5, all divided by x minus 3. So if these two are equal to each other, then that means that the graph will indeed intersect its slant asymptote. So we have to solve this equation. So we would multiply both sides by x minus 3. So in this case, we have a little bit of work to do when we multiply by x minus 3 on the left, because we're going to need to actually multiply this out. So 2x times x is 2x squared. X times -3 is -3x. -3 times 2x is -6x. And -3 times -3 is +9. So look what happens when we start to combine like terms. Notice that if you were to subtract the 2x squared from both sides, the x squared term would subtract out. And if you were to add the 9x to both sides, the x term would also subtract out. So what you're left with is 9 equals -5, which is certainly a false statement. And that tells us, because we got a statement that's not true, that our answer here to the question, will g of x intersect its slant asymptote, is a big no. No, it will not, because we did not get a value of x that showed us where the graph would have intersected its asymptote. So we got a false statement, so my answer is no, it's not going to intersect its slant. So now we have enough information to put the pieces together because these asymptotes act as guides. So I know that my graph is going to have to intersect at the 2 points here that I have listed, the x-intercept and the y-intercept. And it's also going to have to hug this asymptote, this vertical asymptote. So it's going to come over here like so, and it's going to intersect the graph, and then it's going to cruise down here, and it's going to eventually get really close to both the vertical and the slant asymptote. And then same thing on the other side, we have that x-intercept at +5, so I know my graph will have to approach the vertical asymptote. And then again, over time, over time, this graph is going to get really, really, really close to its slant asymptote as well. So you see that the graph has 2 branches. That matches my domain, which had 2 intervals. And we've done a good job. I promise you'll get better at this with more practice. It just takes a bit of practice.